Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
In the previous, video tutorial, in tutorial 62, we developed a multiple regression equation or model for our image collection, where we specified a dependent variable, which were in our case monthly rainfall or participation, and we expressed three independent variables: a constant, maximum temperatures, and wind speed. And we generated the coefficients for our region of interest as a whole, and then for the different pixels or different locations within our region of interest. We then, in a subsequent video tutorial, exported that image, and we generated centroids for each of the locations or the pixels within our region of interest, and we generated the coefficients, etc., for each of those pixels, and we saved it in the attribute file of those points, point layer file, and so we can model it, etc. So the regression functions that we've used applies to image collection up to now. Remember, image collection is a number of images over a specific period of time. Remember, in our case, the Terra climate image collection that we've been working, if I can vaguely remember, is something like 775 or 57 images that's included in that image collection. So this particular regression equation that we generated in video tutorial 62, that coefficients were generated over that 757 images, meaning it's a time series. However, we can also generate coefficients for a particular image. Okay, so not a time series per se, but a cross section. Okay, so in this case, we are modeling similar equation as what we've done in this tutorial 62. Similar equation. However, it's only for a particular image, and therefore it's not a time series, but a cross-section regression. Okay, so that's what we're going to focus on in this particular video tutorial. Remember, we're still working with the same data product or data set, which is a Terra climate. I've mapped it for my region of interest. It's an image collection. Remember, there's 757 whatever images within that. And our time is for this. So now what we've done is we're going from an image collection to a single image. And we do that by using a reducer. And in this case, we're using a medium reducer. And when we can generate a single image. So this particular image, these three particular images are single images using a medium reducer from the image collection. Okay, and we display it, etc. Then obviously here is the script or the code to generate our time series model of our Terra climate data product for this particular model, where participation is a dependent and these are independents, and it ranges over this period. Okay, so this is a true time series regression function. Okay, because we're working with an image collection, you see, we're not reducing it. We haven't reduced this. So you see, it's collection, image collection. We haven't reduced it to a single image at all, because remember, it's collection. You see, we're working with collection. So we're working with the image collection per se. And we're generating the coefficients as indicated here. Remember, these are now the coefficients for my region of interest as a whole. This is the normal linear regression, and it's a robust linear regression. You can see the coefficient for the constant, the coefficients for maximum temperatures, and the coefficients for wind speed. You can see there. Okay, so these are, as I said, the coefficients generated for the image collection, meaning all 757 images. Okay, now let's say, let me go on. Let's say I only have specific images. I don't have an image collection, or I don't want to generate the coefficients for image collection. I only want to generate the coefficient for a particular image, whether it is for a particular month or whether it is for a reduced image. That's totally up to your discretion. In our case, what we're going to do is we're going to generate a reduced image. You see, there's my image collection. Okay, still my image collection. From there's like my data product. Remember the scaling factor, because I work with variables with different scaling factors. We use the scaling factor of the dependent variable. Okay, so remember I discussed that in one of the previous video tutorials as well. Not going to go through this well. So there's my dates format. So this is still. So in the previous regression equation, we used the image collection, this one here, to generate my coefficients. But what I'm going to do now is I'm going to reduce this image collection to a single image using a median function. So therefore, I now have a single image and not an image collection. Okay, so I convert this image, this variable here, this single image, I convert this to an image using the earthengine.image function. Okay, so now I've got a reduced image and I have confirmed that it's an image collection. I've reduced it to a singular image, not an image. See, there's my image collection, which is called collection LREG, collection linear regression, and I've converted that into a single image called image IMG using my median reducer, and it's for this particular period. Okay, so now I've got a single image. So in the single image, I've got a couple of bands, and now I'm going to specify my equation from those bands or those variables. So the first one is I'm creating a constant. Okay, there's my constant. Okay, then and play around with the numbers again. Play around with the numbers and see what it looks like. But remember, the result must always make sense. There must be some logic to it. It must make sense. Okay, then I'm specifying my second independent variable, in this case maximum temperatures, TMX. So within this image that I've generated here, I'm now selecting my TMX band. And I'm saying, I'm giving that a variable name called X variable 1. So by the way, the relevant tutorial that I'm getting this code from, or the script from, is my Earth Engine. Here is the specific tutorial that I'm working from, and I'll leave a description in the, or I'll leave the link in the description so you can find it. Now in this case, they only have two independent variables. In my case, you'll see there's two independent variables. In my case, I have three independent variables. See there's a constant, and there's two regressors, two explanatory variables. Similar as the time series model. This is just cross section because I'm working with an image. So this now regress over this the locations. Okay. So I've got constant. I've got my two explanatory variables here, which is maximum temperatures and wind speed. And I give them each a name. Okay, and again, these names are up to you. But remember, they must be unique. They mustn't clash with other names. And then obviously I specify my independent variable. My dependent variable. Apologies, my dependent variable. And there is my regression equation. It's this image. Okay, and I catastate constant x variable, and y variable. So there's my constant, this one. There is my maximum temperatures, my wind speed, and my dependent variable, which is PR, which is participation or rain. So there's my expression. And then I use my image regress.reduce region, this linear regression reducer, to generate. Okay, so here I'm generating the equation. I'm generating the coefficients. Okay, so this is where I'm going. Remember, it's important to specify these two variables correctly, i.e. My x variables is 3. Now, if you, for example, only have two x variables, meaning a constant and one other x variable, this will obviously be 2. So what they've done here, you can see there, they only have two x variables, or two independent variables. So they only have 2, not 3 as in my case. Now, I can have 4, I can have 5. You just continue. So you can call it x variable 3 is equal to im.select whatever the variable is. You can put, let's say, minimum temperatures in. So let's quickly have a look and see, just for interest sake, what other variables there are. Climate. Let's see what other possible explanatory variables we can include. Okay, so let's have a land band. Soil, no, that's not going to, soil, downward surface, shortwave radiation, snow, water, that's not going to work. Vapor, that's not going to have an influence on participation. I can't see any of these things. So most probably that's basically the explanatory variables that you can, but you can use, you can specify different equations from all of these ones. That's totally up to you. Anyway, I digress. Okay, so there we are now converting our coefficients. Remember here we're generating our coefficients from this equation. Okay, so we're generating our coefficients, and here we are basically just putting our coefficients in a list. You see, they to the list. And now we extract the y and the slope coefficients. Now in our case, we will have a constant, and we'll have two slopes, okay, or coefficients. We'll have a maximum temperature coefficient, we have a wind speed coefficient. Okay, so what we're saying here is from this list, okay, get the coefficients from this list. Remember, that's coefficient there. Get the coefficient, so meaning here, okay, remember, what is get 0? Get 0 means the first value in the list, okay. Remember, that is now, remember, it starts from 0. So 0 would be the first value. 1 would be the second value. 2 would be the third value, and so forth, and so forth. Okay, and get 0. The last part here is the equation as a whole. So what we're saying is get the first value in my equation. Get the second value from my equation. Get the third value from my equation. And what is the first value? The first value will be constant. What is the second value of my equation? Will be x variable 1. What is x variable 1? X variable 1 is maximum temperatures. Okay, so basically the first get here is the number in the list. Remember, the list starts from 0. It doesn't start from 1. The list starts from 0. So 0 is the first value in my list. Okay, and remember, we've converted these coefficients in using this into the list. And this last get 0 is the equation as a whole. So that's what we're doing here. Remember, in our case, there will be two slope coefficients. There will be a slope coefficient for maximum temperatures, and there will be a slope coefficient for wind speed. Remember, get 1 is our second variable. What's our second variable? X variable 1. What is that? It is x variable 1 is maximum temperatures. Okay, and that's a median value. Okay, for this period. Anyway, so, and then we basically just calculate the residuals. Okay, so we're generating residuals as well using this. So we're getting, to get the residuals, to get the list, remember, get list is this list, and we're getting the function as a whole. Okay, so getting the function as a whole. And then we're just printing our coefficients. We're printing all the coefficients, and here we're printing individual coefficients, including the residuals. And then we basically just press run and we save. Okay, so what will be the output? Remember, this is a cross-section regression because it's based on one image. So the coefficients will be determined by the number of locations within, or pixels or cells within my region of interest. So if my region of interest has 400 pixels or 400 cells, then these coefficients will be generated from that 400 pixels or cells, not from time, but from cross-sections. Okay, so remember, in our image collection, in our time series, we've got the constant coefficients, we've got the maximum temperature coefficients, and we've got the wind speed coefficients. So we've got those coefficients working from our constant. Remember, they are now over 757 images. Okay, so let's quickly see what our coefficients are from our single image, from our cross-section image, this one here. Okay, so we've got our, remember what is 0? 0 is our list 0, is the first item in our list, first value in our list. Our first value in our list is our intercept, B0. See there? B0 is our intercept. What is our B1? B1 is our second value in the list. What is our second value in the list? It is maximum temperatures. Maximum temperatures. What is our third value in the list? It's wind speed. It is wind speed. Okay. So we've got a constant, our maximum temperature coefficient, and our wind speed coefficient, and then we have our residuals. Okay, so that's the three that we are calculating there. Okay, so let's have a look and see. So compare it to our time series. So we've got a coefficient, a constant coefficient, which is much less than the constant coefficients for our time series, much less. And there could be a number of reasons for that. I don't think that's too much of an issue, whether it's a little bit more or a little bit less. That's not really an issue. The constant is generated, as I said, for that particular image, whereas this is for images in the time series, and there could be a number of reasons why there's differences. But I'm not too stressed about that. That's not an issue for me. Let's have a look and see our maximum temperatures. In this case, our maximum temperature is minus 0.13. In the previous two, it's minus 0.5, minus 0.4. So they're in the same decimal range. Okay, so they're in the same number range, which is good. You don't want them to be totally different from one another. For example, this one here being minus 6,000, and this is minus 0.4. Then you know there's something wrong. But in the same decimal class or decimal range. So that gives confidence. And again, it's a bit higher. That could be just because in that, remember we were using a median reducer. So there could be reasons that the median, we can try the mean and see if it looks a little bit different. So remember, in this case, what do we use here? No, we don't use reduce because we're using the actual values itself. So, no, so we don't use it there. Okay, so let's have a look at the wind speed. And okay, there's the wind speed. Again, same reduce, 0.05, 0.04, 0.04. So it's in the same decimal class as well. So that's, but look at the sign. It's totally opposite. So here there's a positive relationship. Here there's a negative relationship. So the same decimal range, I'm happy with that, just the sign changes. Okay, so it gives me confidence that the numbers that we've, coefficients that we generated looks very similar. And there's the residuals. Okay, so let's quickly take these numbers and I'm going to copy it into our Excel. Okay, I'm going to copy it into our Excel, and there they are. And let's see if we use a mean function, what the numbers look like then. So let's not use median, let's use the mean reducer. And let's see what our coefficients are now, and then we can compare it to our time series coefficient. So let's quickly press run again. And remember, if you press run, press save. Run and save, run and save, run and save, run and save, all the way. Okay, so we're just waiting for those coefficients to generate. Should sit under here. We've got our normal OLS and robust. That would be independent of what I've done now because we haven't changed anything. Okay, here we go. Let's see, coefficients. Okay, so let's copy that. I can already see some differences, although it's really very, very small. It's not making a much of, okay, it's not making much of a difference. 68 to 76. Remember, this is median. Let's make it bigger. Remember, this is median and this is mean. So this would be median, right, of median, and this is mean. Okay. Let's make it bold. Okay, so let's quickly, I'm going to just delete these numbers that we don't actually need. Okay, so we don't need, so 3 elements. So let's just delete that. We know what the numbers is, so we're going to delete that. Okay, so that's coefficient, constant to constant, not too much of a difference. Maximum temperatures to maximum temperatures, not much of a difference. Wind speed to wind speed, still a minus, not too different, and the residuals are in the mean higher than in the median, so by definition the mean is a better, or the median is a better reducer than the mean. And I think this is a recurring theme. Doesn't matter how you look at it, the median reducer seems to be a better reducer than the mean in general. So let's have a look and see. Well, I'm not going to do sum because we're going to get extraordinary numbers if we do the sum. We can do min. So we can generate a min number there. Let's run it again. I'm not going to save it. Let's save. I can always convert it back. But anyway, you can play around now with this reducer in order to see, to minimize your residuals. Okay, and obviously by minimizing your residuals, you improve your overall accuracy of your model. Okay, so let's have a look and see what the minimum is not working at all. So let's go back to mean and stick with the mean function. As we've already, as I said, identified. So if you want to add more explanatory variables, you can do that. If you want to have less, you can do it. Just remember, if you add it there, include it in your variable here, your equation here. Make sure you add it in your regression function here, and then obviously in your extraction of your coefficients. Okay. So I hope that makes sense. As I said, the big difference, obviously, what we've done now is we worked with a singular image. So it's a cross-section regression, whereas in this one here we work with this one here. We work in a time series format. Here we work in a time series format. So this is because we work with an image collection. So if you work with the image collection, it's time series. If you work with a single, it's cross-section regression. Okay, and again, what we can do is we can generate all of these we can apply this now in let's say in QGIS. We can play with the model in QGIS to do predictions, etc., etc. Or in fact, you can move it into Excel, like what we've done here. You build your model similar to what we've done in this previous video tutorial. You can build your model in Excel and then put in hypothetical maximum temperatures, wind speeds, and then generate what the rainfall would be if for those particular parameters for your explanatory variables. So that's what you can do. Okay. Well, thank you. Yeah, thanks for joining me. That was nice having you on board. Look forward to your continued presence on this journey into remote sensing. Thoroughly enjoying your company. Please feel free to share this video, to like this video. Please subscribe to the video. And yeah, stay tuned. I'll see you on the other side.